this slide here assume that the discount rate is constant. Again, this equation here is showing, the yellow one here is showing that the discount rate is constant, right? Now, what does that mean, discount rate is constant? Well, the bank is paying me, if I put my money into a bank saving account or GIC, something like that, it pays you maybe depending on the type of account, depending on the type of investment. Let's say you might get 1% or 3%. But this interest rate, is it going to stay the same forever? No. The interest rate fluctuates all the time, right? Not even 1 year, a few months. The Bank of Canada will adjust the rate, right? Okay. So what if the rate change? Well, again, let's assume the rate will stay for 1 full year and then next year change. It doesn't change every few months. Let's assume that, right? But even with that, now we can write the value of the present value. Yeah, the present value is future value divided by 1 plus R1. This R1 is the interest rate or the discount rate for the first year. If second year the rate change, then instead of 1 plus R bracket square like the one we have up here, right here, now it's 1 plus R1 times 1 plus R2, where R1 and R2 are the rates in year 1 and in year 2. And of course, if they are the same, it becomes this 1R and this expression there. For the third year, now you should be able to see the pattern now, right? You have one extra terms, 1 plus R3 right there. That's the rate for year number 3. Right? So if every year the rates change, you have a similar, a slightly different expression. The discount rate is basically the price of money. Again, the discount rate is the price of the money. It tells us how much future cash is worth today. It's affected by several factors. The interest you could earn elsewhere, like for example, if I don't invest the money in an energy project, I can put it in the bank, and then the bank will pay me interest, right? And it can also be affected by the inflation and also the risk of uncertainty of the project. If the project is risky, right? If the project is risky, then you might want to say, you know what, this is risky. I need you to, it costs more to do this kind of project because it's risky. Okay. What else can it affect the discount rate? How easily you can get your money, right? If you can get a fund easily, then yeah, it doesn't cost much. But if it's very difficult to get the funding, then that cost becomes higher. You need to increase the discount rate to reflect the difficulty to get the money, to reflect the uncertainty that you are facing. Sometimes even government policies as well, right? Government policy. So by considering all of this, the discount rates tell us fairly how we compare future cash flow to today's investment. Okay. Net present value example. So using a discount rate of 5%, calculate the net present value for the cash flow example. Okay, let's do the example. I'm going to write the equations down here. PVN equal to Fn divided by 1 plus r brackets to the power of n. The present value of that after so many years, which of fn is equal to fn divided by 1 plus r to the power of n. So first one, PV1 and F1, what's F1? Minus 35. That's the expense. 1 plus R is 5%, so 0.05 to the power of 1. And that's equal to minus 33.33. PV2 equal to, what's PV2? I have 10 units, positive 10. 1 plus 0.05 bracket square equal to the number I have 9.07. And PV3 is also 10 because 15 minus 5, the net cash flow is positive 10. So I will write 10, 1 plus 0.05 to the power of 3. The answer I have is 8.64. Okay, this is 10. Not very clear, right? Not very clear. 1.05. Okay. Anyway, it's plus. And PV4. If you do the same, PV4, you will get 4.11. Why? It's 5 divided by 1 plus 0.05 to the power of 4. Okay, this color is not very good. Change. But hopefully from the first two you can see the pattern, and the number here you can check. All right, so total net present value is equal to minus 11.51. So net present value is negative, not good, right? Not good. All right. Now, on the next slide, it says, do the same calculation for 10% discount rate. So please do that. And we can check the numbers when we meet. The net present value for this example here, 10% discount rate, it's minus 12.63. Minus 12.63. See if you can get that number. All right. So after you get that minus 12.63 compared to the 5% discount rate, minus 11.51, right? So it's about a little bit more than 1 unit of difference. What's happening? Well, we increase the discount rate from 5 to 10%. We are punishing the future savings, right? We are actually punishing the future savings with that extra 5% of rate. So here we have two projects and two reference investment rate, or what they call vehicle here, right? The rate term CIBC GIC is 1.25% for 5-year term. The Toronto District School Board debentured 5.07%, 20 years. So project number one, lighting retrofit, replace lighting system, cost $5,000, annual savings $1,000, and therefore SP, simple payback. Simple payback is the initial cost divided by the annual savings. Therefore, 5 years. 5 years payback. Okay. Second project, boiler replacement. Initial cost is $100,000, but the annual saving is $8,000 per year. And if you divide 100 by 8, you get 12.5. So simple payback for project number 2, 8.5, 12.5 years. 12.5 years. Okay. Now, if we use the net present value, like if you do a cash flow diagram, 5,000 in the initial cost and then 1,000 every year for the next 20 years, and you do the present value for all the savings and the initial cost, you get 5,810 if the discount rate, right, the R term in the equation is 6%. If it's 5%, it's a little bit higher, 6,678. 2.5, even higher, right? The net present value. Why? Does that make sense? The discount rate goes down, but the net present value goes up. Makes sense because the discount rate, it's punishing future values, right? So the lower the rate, the higher the savings. Now, does that make sense? Think about that. Maybe I should think about how I should say it. If you look at the boiler, similarly, you do the cash flow diagram and then convert all the future value to present value. The sum of the present value. For 6%, it's negative. For 5, also negative. A little bit less, but also negative. And for 2.5, it becomes net positive. Does that number make sense? Well, 6%, about 10,000 minus 10,000 approximately. Okay, but if we decrease the discount rate, we punish the future savings a bit less. Therefore, the future savings give us a higher present value, and therefore becomes less negative. And if you reduce the rate to further to 2.5, it becomes positive. Okay, now the two vehicles. If you put money in the bank CIBC in 2016, the rate of return is 1.25% for 5 years. And let's assume, see, you can see the point now. You can very likely after 5 years, the rate will change. But now let's just assume it's 1.25 for the next 20 years. Okay. And the debentures, right, that TDSB issued is 5.07%. So the question is, the TDSB considering a non-essential lighting retrofit as part of an energy management program in 2004. Will you do it? That's the question. B, a homeowner deciding between a GIC and replacing an old boiler. Would you replace the old boiler if you are the homeowner? That's the question. So how do you decide? How do you decide? Think about it. Think about it. Okay, let's take a look. TDSB, Toronto School Board. Now it's non-essential lighting retrofit. If they raise the fund, they have to pay 5.07%, right? And that's for 20 years. If they replace the lighting, net present valued 6% is 5,810. 5% is 6,678. So at 5.07%, at 5.07%, what does that mean? It's between these two, but it's closer to 5. And this is 5% right here compared to the 5% there. Even at 5%, it gives the project a positive net present value, 6,678. So that means, right? For TDSB, it's worth the investment. It's worth the investment. Not much, but still positive. Okay. Now, if it's, let's say, a boiler that the school board has to replace, between lighting and boiler, which one should the school board choose? Think about that. Maybe we will talk in the class during when we meet, just to check. Okay, and answer the question and just to check. Similarly, for homeowners, I mean, here we're deciding GIC between a GIC and an old boiler, but we can also look at both projects. Let's say the homeowner has a similar situation, both projects. Should the homeowner put the money into this project or into the bank? Think about it. Internal rate of return. Internal rate of return is the interest rate your project earns. That's the project. In a project, if you can make 5% return over so many years, your internal rate of return would be that percentage. But what does that mean? Right? Let's say if the internal rate of return is 15% and the bank give you 5% if you put the money into their bank, what would you do? Do you do the project or do you put the money into the bank? 15% or 5%? Of course, you want that 15%. Right, 15%. And energy project, in general, they are, well, depends. But let's say energy project, they are low risk, unlike maybe stock compared to stock market. If you install a VFD, variable frequency drive, the savings are almost, when I say almost, it's because it's not always, almost guaranteed by physics. If you do it right, maybe. If you do it right, you get savings. That's no question, right? If it goes wrong, then there's something with the design. But let's say if we design it right, then it almost guarantee you savings because you can do the calculations, you know the physics. So if you are the chief financial officers, right, you will accept a lower internal rate of return for energy project than for new product because it's a higher risk. Okay, so it really depends. It's not just the rate of return, it's the risk, the uncertainties as well. But internal rate of return is your rate of return on investment. Okay. And as you mentioned, the it represents the discount rate that we saw in net present value equal to 0. Right? So another way to think of it is how the what would be the discount rate be so that all my future values, when I convert them into the present value, everything sum up to 0 at the present value. We want that percentage. That's why I was using the interest rate that the bank is willing to pay you. Right? Okay. Life cycle cost analysis. Or sometimes you might, in the literature, you'll see LCCA, right? Looks at the total cost of owning and operating an asset over its entire life, not just the purchase price. It includes the initial cost, operating and maintenance costs, repairs, replacement, disposal, and account for savings like energy efficiency or rebate, right? Essentially, the life cycle cost analysis is the same math as net present value. You discount all future cost and future savings to today's value. If you only include cost, the life cycle cost analysis shows the total life cycle cost. Right? If you include savings, it becomes a net financial impact. Okay, where a positive result include maybe it indicates the project. How should we say this? If you include savings, it becomes financial impact where a positive result indicate the project adds value, right? If only if it's positive. If it's negative, then the overall, no, it's not good. So life cycle cost analysis help engineers, building managers, and homeowners make informed long-term financial decisions, comparing alternatives fairly and accounting for both cost and benefit over the project life or the equipment life. Okay. LCCA look at the whole story: purchase, maintenance, energy, and even the end of life, the scrap value. Okay. In Canada, the carbon tax, right, is scheduled to increase every year until 2030. It's changing all the time. But how, in any case, right, how does a carbon tax change the life cycle cost analysis of say a gas boiler versus an electric heat pump? Okay, the operating cost of the gas boiler will go up if there's carbon tax. All right, if there's carbon tax, and so and the heat pump will stay relatively stable, right? Relatively stable. The cost of electricity might go up, but compared to carbon price, because it's imposed by government, then the price of a gas will most likely go up. This is often the only way to make heat pump look better in the life cycle cost analysis. Okay. But heat pump is doing better and better now. Hopefully. the cost, if the life cycle cost analysis focus on costs, that's the traditional LCCA, most common in public works, building design, and asset management. It focuses on total life cycle cost only, how much it's going to cost me for the whole life cycle, right? That's cost. And the cost on operations, cost on maintenance, replacements, and salvage, right? When used when comparing alternatives that don't generate revenues, right? If they don't generate revenues, then well, which project will cost me more? Okay, cost me more. So the goal here, the goal is to choose the options with the lowest total cost over its life. Net present value styled life cycle cost analysis with savings, let's say. And it's common in energy efficiency, sustainability, and retrofit projects, because those projects usually will generate not revenue but savings, right? Savings, energy savings, rebate, or scrap value. And the goal here is to see if the investment actually adds financial values, right? Lighting retrofit that we talk about all the time, or the high efficiency boilers, right? High efficiency boilers. Okay. Excuse me. Okay, on the last slide, we have this alternative investment example. Two boiler systems, they are considered system A or system B. The selection will be made based on the life cycle cost analysis with discount rates 10%. The first cost 80,000 for system A, 35 for system B. System A can last for 20 years and 10 years for B. So for system, if you do system B, then after 10 years, the system will be replaced, right? Will be replaced, and this is the cost. At the end of the life, system A also has a value. So this is positive for system A after 20 years, though. After 20 years, additional cost, 1,000 for the first 5 years for A, 1,500 for the year 6 to 10. Year 10, system A need to replace the burner, because it's need to do every 10 years. You need to do replace the burner, and that's the cost, 5,000 at year 10. After year 10, year 11 to 20, $2,000, because now the equipment is old and you need to spend more to maintain, repair. Okay, so that's for system A. For B, 3,000 for the first 5 years and 4,000 for the next second half of the year 6 to 10. And of course, year 10, you will spend 35,000 again to replace the whole system. So do this example and see if I can give you the answer now, but we will look at this in the classroom. Where's my... Okay, so for system A, the total present value, see if you can get this number, is minus 92949. For system B, I get total PV equal to, and here is equal to minus 77302. So that means alternative B is cheaper over 20 years. Over 20 years, alternative B. They are both negative, but now if you have to choose one, B is still better. But in any case, try this example and see if you can come to these numbers. Right, just quickly. First cost, 80,000. So what would be the present value? Minus 80,000. Okay, because that's right now. Year one, at the end of year one, you have this additional cost, 1,000. So minus 1,000. But minus 1,000 in 1 year, what is the value right now? That would be minus 1,000 divided by 1.1 because it's 10%. For the second year, 1,000 divided by 1.1 to the power of 2, 1.1 squared. Right, and then you do the that for all the years. That's an equation, but we're not going to use that. Just stay with this equation that we discussed here, okay, and try to solve that. Might be yeah, it's long because 20 years. Okay. That's it for this module. So I'll see you in class.